Yeah, welcome everyone to our third lecture, Research in Financial Markets. And the third lecture is entitled On the Second Moment of Financial Assets. I'm actually wondering, what my colleagues told me that about 80 people or 85 people are for this, who have registered for this course, and I just see 10 here, or 9. I was wondering where all the others are, right? Because that's an in-class lecture. So I mean, if you work at the bank, okay, if you do not attend to your job, I mean, first time you get a warning, second time you get a warning, and third time, you know, that's it, right? I mean, so I don't really understand, because obviously that's your job description, and unless you can understand everything by yourself, which is, I think, impossible, because that is not that easy what we talk about here. So I mean, I'm wondering how the others will want to pass this course. I mean, I don't know. I mean, because they have to also solve my part from the assignment. My part in the assignment should be related to data analytics. So you have to understand the concepts here, right? So I don't know if it's possible without coming to the lecture. Maybe it is. I don't know. But yeah, I'm just a little bit surprised, because it says in the instructions it's an in-class lecture. I have also online classes that you can take via distance, right? And then, of course, then they are constructed in a way that you can learn that without coming to lectures, because there are no lectures, they're online. But here, it should be in class, and that's why I set it up like I did. And we got actually like a directive from the rector that we should teach in class certain courses, and this is one of these few courses that actually are in class. So yeah, so what's the problem here? Let's start with the problem. Well, if you have first of all, we have now a new heading here, a subheading. The earlier heading, you might remember, that the student is not above his teacher. We were talking about Farmer and who won the Nobel Prize, but his research failed scientific replication. It doesn't hold in expanded samples. It does not hold in other local economies and so on. But he won the Nobel Prize for that. Okay, so and his doctoral thesis supervisor, Benno Mandelbrot, he did not win the Nobel Prize. But if you have Googled him, he won a lot of other awards in mathematical science. Yeah, and his findings actually hold in expanded samples and also in different asset classes. Okay, I have a paper, quite many papers now on that topic, studies, and I can show that actually, yeah, if you have foreign exchange rate market, the G10, the G10 currencies, and you estimate this exponent for a certain subsample, you get statistically the same exponent for the expanded sample. Yeah, so it's sort of you can replicate it, and it holds. The result holds in expanded sample, so you can actually work with it. But you cannot work that much with what people have documented in the asset pricing literature or corporate finance literature. Okay, well, we'll talk about it. So there's a study from Hu Xu and Xang. Quite recent study from 2020. It's published 2020, but of course they worked on that already in 2015 or so. Okay, this is usually how it goes. Okay, in academia, so it's a very slow process. Okay, you work on something, and then you have to present it at different conferences, get feedback from your peers, and you have to make a revision. You have to do change some of the analysis or do other robustness checks and so on and so forth. So it takes a couple of years. But not always. Okay, some of these studies take a couple of years, but not always. So they investigated 452 asset pricing anomalies. Okay, like different kind of momentum anomalies. Okay, we have this time series momentum, cross-sectional momentum, short-term reversal, profitability, value. So you have obviously even for the value strategy, you have different kinds of anomalies. Okay, that can be summarized above the heading value anomalies. Okay, but there are different ways how to implement the value strategy. Yeah. Well, anyway, so these 452 anomalies have been reported, have been documented or derived from 111 research papers, and most of them published in these top-notch journals. Okay, where also Farmer published his studies, and for which he got the Nobel Prize. And they argued here, okay, because finance is exposed to sort of data mining. Okay, so if you have figured out something, some strategy or whatever, you usually get it published, or it's more likely to get it published if you have a positive result. If you find something, okay, if you find some new risk premium, okay, some new strategy that somehow generated a payoff. Okay, if you do not find something, it usually does not get published either. So. And that's why they argue because of this data mining, okay, the standard t-statistic you should have a higher t-value in order to talk about significant. So we talked earlier about the critical value of the normal distribution. We talked about it last time as well. So we have the normal distribution, and you have this 1.96, okay, and you have a positive payoff. Okay, that's obviously what you want to exceed with the t-statistic. So, but because of this data mining or data snooping, you should have a much higher t-statistic. So you should exceed 2.78. Okay, this should be your value where you can talk about statistical significance. So, and this was actually proposed in another study, okay, from Harvey, Liu, Stewart, and these are all these guys they usually publish only in these kind of top-notch journals, okay. So people believe because it's published there, it's the truth, okay. Yeah, and as I already said, so from these 111 studies, okay, the vast majority is published in the Journal of Finance, Review of Financial Studies, or the Journal of Financial Economics. So, and what they figured out is that 82% of these 452 asset pricing anomalies it's just noise. Yeah? You cannot replicate it in extended samples and of course then you may wonder, okay, I mean these kind of studies or phenomena are documented in what people think is the top-notch science. Yeah? So why do studies fail to replicate? So they argue that, okay, authors sometimes engage in specification search, selecting sample criteria and test procedures until insignificant results become significant. This is called p-hacking. This is actually data mining. Okay? And this could result in an embarrassing large number of false positives. Yeah? So positives, you find something significant, but it is actually not. It is just noise. But this is what it means. And therefore, these results cannot be replicated in extended samples in the future or in other geographic environments. However, there could be also another reason for why studies fail to replicate. And it could be that if the variance of the data generating process variance does not exist, a t-statistic will become sample specific. Yeah, because the theoretical mean, like we discussed last time, we need, was it 1 million observations, right, until the theoretical mean actually converges to something reasonable. So that's the problem. So in every sample, you will get a different variance, and what we will see is that the t-statistic depends on the variance. It's sort of a function of the variance. So in empirical finance, and the estimated t-statistic for a specific sample is computed like that. Let's say we investigate the value anomaly or any kind of strategy that has some positive payoff. Okay, you usually test if it's significant. And what do? Okay, you take the sample average. Let's say it's 0.5% per month or something. And this mu is usually 0, okay, because you want to test if it's significant. And then you divide it by what? You take the observations, so the sum of the observations minus the sample average squared, and divide it by t. So that's the standard deviation, right? And then you divide it by the square root of the number of sample observations, capital T. So if we have, okay, and we know from statistics that any normally distributed random variable you can transform into the standard normal, right? You just, what do you have to do? Let's say x or let's say y is some normally distributed random variable. Okay, what do you have to do? You have to compute. You take each observation, subtract the sample mean and divide it by the sample standard deviation. Okay, that guy here is normally distributed with mean 0 and variance of 1. You can do this for any normally distributed random variable. It's just how it is. So if we take, let's say, if we do that for our variable as well here, what is here, that's a random variable as well. And we talked about last time, okay, so we know if we have the standardized random variable, x bar is 0, right? So what we have is the squared norm is a squared standard normal. And what's the distribution? It's a chi-squared distribution with 1 degree of freedom, right? So this is basically how it should be if we are in the Gaussian world, and if the standard assumptions in finance theory hold. Yeah. So the denominator, and here I write in the lecture notes chi square 1 distribution or chi square 1 type distribution, because of course if we use the non-standardized series, okay, it will not be exactly a chi square distribution with 1 degree of freedom, yeah, but it will behave like it. It will have the same behavior. So, and you know, for the chi square distribution with 1 degree of freedom, and this is actually the correct version here. So in your slides, there's sort of there's a typo. Okay, so because I divided everything by square root of t, and that's not necessary here. Okay, so this guy here. So if this is a chi square distributed random variable, okay, then we know that the expectation should be k. Yeah. So if we have only like it is here, like one asset, yeah, and here is the asset minus the sample mean squared. So chi squared distribution is 1 degree of freedom. So k is then 1. Huh? Second moment is also clearly defined. It's 2k, very simple. 2 times 1 is 2. Yeah. Third moment, which is the skewness, is also clearly defined. It's the square root of 8 over k, and k is 1, so it's square root of 8. Fourth moment is also clearly defined. It's 12 over k, and so it's 12 over 1 is 12 plus 3 is 15. So kurtosis is 15. So all these moments are clearly defined, so we can operate with it. So this, because this is defined here, the fourth moment is defined, and second moment is defined. So this guy here will converge to something. It will converge. If you have a very large sample, it will converge to the true value. Actually, most important is here that the second moment is defined. Okay, second moment is it's all the other. I mean, of course, it's econometric, but the most important here in our framework is, okay, the theoretical mean of what is here, that is defined. If you have a very large sample, it will converge to the true value. And the second moment is also defined. The second moment means, okay, the variance of what is here also exists. So it will not explode. So your result will not be sample specific. Your result will not be sample because because the second moment exists of what is here, it will in finite samples converge, and you can operate with it. Now, the variance of variance exists, so this will not be sample specific. If the sample is large enough, you can operate with it. So I have written a study. The study is entitled, "What do we know about the second moment of financial markets?" Yeah, and what did I do in the study? Well, I explored the distribution of annualized daily variances of 5 asset markets. Yeah, I think I use S&P 500, gold, oil, Bitcoin, and the foreign exchange rate, the British pound against the dollar, right? So 5 very important asset markets. And I used the intraday variance or range-based variance estimator from Parkinson, okay, which uses the, and there's actually parentheses missing here, all right, so there should be in parentheses. So it's actually, let's take this away, because, you know, I teach this now the first time, because last year I was on paternal leave, all right, and the year before I was teaching different stuff. Yeah, so to this year I'm teaching this new stuff just for you. So it's t times 1 over 4 times logarithm of 2 times, parentheses, the logarithm of high minus logarithm of low. We close the parentheses and take it to the power of 2. So we square that. So that's the correct formula, okay? So this is what I computed. Or to get the data, you can get data from Bloomberg. We have this Bloomberg lab here. I don't know if you know that, so you can use it. And you have also other sources. You can use investing.com. They have quite reliable data. Yahoo. Some people use yahoo.com. They have also intraday quotes of foreign exchange of many different assets. So quite easy to compute. And there are different range-based variance estimators, okay? But in the end of the day, you know, they are very, very similar. So it doesn't really matter. So if you write a study, okay, if you work in academia and you write a study and you use this kind of estimator, then and your study goes under review, then the reviewer will a little bit complain, because he has to complain somehow, and he will then tell you to use a different range-based estimator. Yeah, but the results will not change because they are so similar. But yeah. Some people use other range-based estimators, but it's all the same. So, and here in table 2 of my study, you can see I computed the top 1% of largest observation from this variance estimator on the cumulative, so the share on the cumulative total of the distribution. So. And we see here, for the S&P 500, it's 21%. So 1% of the largest observations make out 21% of the total. If this would be normal, it would be 3.6%, like we discussed last time. For gold, it's 19%. It's almost the same. For crude oil, it's 23%. For the US dollar, it's 73%. And it's actually the British pound, right? And for Bitcoin, it's 18%. And the interesting thing is, if this would be a chi-square distribution with 1 degree of freedom, the top 1% of the largest observation would comprise 8.46% of the cumulative total. Yeah, so we see it's obviously the variance is not distributed as a chi-square type distribution. Yeah, the tails are much fatter. Yeah. And one thing that we discussed last time, yeah. So you might remember that I showed you a graph where we have seen the compounded return of the S&P 500, and I showed you that 1% of the largest observations make out about 50% of the total of the total compounded return. If you do the same thing for the momentum strategy, I assume that you know what it is, right? Momentum. I think it's some sort of basic stuff, right? So if you do the same thing for the momentum strategy, you will see that 1% of the largest observations make out. What do you think? You may have a guess. %. Even slightly more than 90% of the total. Yeah? So the strategy is driven by extreme outliers. So just as you know. So okay, the research question was here. Okay, do realized asset market variances exhibit power law behavior? Because obviously the tails are so extreme that the standard distribution cannot capture that. Okay. So again, I use this function that we already have seen earlier. Okay. X minimum is the minimum value of the realized variance that is governed by the power law process, and alpha is the magnitude of the tail exponent. So there are different ways to estimate that, to get the corresponding exponent. But that's the important thing, okay? Because once we know that, we know how the distribution will behave, okay? Also in expanded samples. So what they did in physics, I told you already, there's this book from Geoffrey West entitled Scale, and the whole book is about log-log regression. This is what physicists are usually doing. That's the traditional approach, okay? You have the P from X is what? It's C, capital C, times X to the power of minus alpha. So what people are then doing in physics, so they take the logarithm. We have then ln from P from X is what? It's the logarithm of C, okay? And we know the roots for the natural logarithm is then minus alpha times the logarithm of X, okay? Then we can, because this is then a kind of linear regression model, okay? We have to add here the error term epsilon. So what people then are usually doing, they employ linear binning. So you sort your data vector. Let's say you have observations. They start at 0, I don't know, and they go until 1,000 or so. That's the highest value, and then they divide it into, let's say, 10 different bins. Okay. So from 0 to 100, from 100 to 200, from 200 to 300, and so on until 900 to 1,000. Okay. Because these are the values of your observed realizations from X. And then you count the number of observations that are between 900 and 1,000. That's then one bin. You count the observations between 800 and 900. That's another bin, all right? And that's then sort of the mean is the 950, right, for that bin. You take the logarithm, because it's logarithm from X, and then the number of observations that are in that bin, it's maybe, I don't know, let's say it's 15. You take it, that's then the corresponding probability. Because it's 15, and let's say you have, I don't know, 100 observations, then it's 15 over 100. Okay, it's 0.15. Logarithm of 0.15 is then the corresponding ln from P from X. And you do this for all the other bins as well. Okay, and then you have 10 observations, 10 bins, and you can implement this linear regression model for these 10 bins. Yeah? That's then the y, that is then the x variable, and then you just run the linear regression model, and then you get the estimate for alpha, for the power law exponent. That's what people have been doing, okay? And of course, there are always improvements. So one problem here is that this methodology suggests what you know from from basic econometrics that you assume that they're independent, right? So that's already one problem. But yeah, so that's what people usually have been doing. But there's another methodology that's the maximum likelihood estimator. Yeah. So you have this maximum likelihood function where you can estimate the exponent like you have it here. Okay, it's 1 plus number of sample observations n. N is now different from t. Okay, because obviously, let's say if t is 1,000, we have 1,000 observations, but only 30% are governed by this power law. Then n is obviously 300. Okay, so it's less than capital T usually. And then we have, okay, we take the sum of what from I equal to 1 until capital N, the logarithm of xi over x minimum. And we take only the values here of the distribution that exceed the minimum value. Yeah, so we can do that. So what we do here is we sort our vector in increasing order, or decreasing, it doesn't really matter, but it needs to be sorted. Okay? And then, let's say, here's the first observation, x1. That's the lowest observation, the lowest value. And here we have x, capital T, and that should be then the highest observation in the sorted vector. Yeah? And we can take every value here as the corresponding x minimum, yeah, and do this iteratively. Yeah? And what we then get is we get a whole distribution. So here is the x minimum, and we start with the lowest number here, x1, okay, and until the highest number, x capital T. And we get the corresponding, we can estimate the corresponding exponent here, which will be a function of the minimum value that we choose. That's the maximum likelihood estimator. And this function will have a certain shape. So if the data is well behaving, which you usually never see in real life, but it will look like that. You know this probably from high school, sort of this kind of curve, and here we have somewhere the saddle point. The saddle point. This is the point where the derivative here is close to 0, or it should be 0. Yeah? And that's the place where the optimum is. That guy here, this alpha hat that is related to the saddle point, is usually the corresponding value that you choose as the optimum. So you can, via visual inspection, actually already see or determine what is the optimum for the corresponding power law exponent given your data set. Given your data set. If the data is well behaving. So, and once again, so we get a whole bunch of estimators here, okay? The maximum likelihood estimation means, okay, for each of your observations, okay, that you take as your minimum value, you will get a different power law exponent, alpha. And the tricky thing is to determine, okay, what's the optimum here? Which to choose, given the data set. So here is the hill plot, and this is called hill plot, okay? If you plot the alpha here, depending on the corresponding minimum value, which is what I have done here, that's called the hill plot. And this is what I've done here for the S&P 500. Quite well behaving, right? It looks quite like that, right? S&P 500, variance of the S&P 500. So somewhere here will be the saddle point of that function, right? But we do not know the exact value. And that's what we want to know. So again, Klaus et al., so the authors, yeah, they who proposed a new approach how to determine the corresponding minimum value for x and also the corresponding exponent. So they argue, okay, it's common practice to choose the value for x minimum where beyond which alpha hat is stable. Yeah? So here somewhere. But from the figure 5 in the paper, it can be observed that this value corresponds to the saddle point. Yeah? So therefore, somewhere here, there's a saddle point, right? But we do not know exactly. And that's a tricky thing. So the authors, they propose an approach that chooses the value for the estimate x minimum that makes the probability distributions of the measured data and the best fit power law model as similar as possible above x minimum. And then it's obviously called x minimum hat because it's then the estimate. So since the analyzed data is not normal, the authors make use of the Kolmogorov-Smirnov or KS statistic, which is the maximum distance between the cumulative density functions of the data and the fitted model. So what does that mean? So let's have a look. So for every x value that you take as the corresponding x minimum, okay, you can estimate the corresponding empirical cumulative density function. Yeah. And it looks maybe like that. And then you estimate given your estimated alpha and x minimum value, you can simulate or you actually can compute the corresponding value of the cumulative density function of the real value if the function would be true. And it maybe looks like that. So the maximum error that you do here, you see here, it's probably here. That's the maximum error, the distance between the cumulative density function, the black line, and the empirical density function. So that's the maximum error. So you collect this guy here. The distance is maybe, I don't know, it's delta 1. Let's call this here D1, okay? Let's call this here D1. And we collect it here. Then we do the same thing again, but then we take the next observation as our corresponding x minimum value. Again, we compute the empirical cumulative density function, and we compute the corresponding values that the hypothesized power law function would give us, if this would be the true function behind this data generating process. And again, we check what is the largest error that we do, and we collect it. That's then our D2. Okay? And we do this for all data points that we have in our sample. Yeah? So from D1 to until D capital T. And what we take then is, okay, after we've done that, we search for the minimum value of this D. What is the minimum value of D? So it's sort of the minimum of the maximum errors. And we want to minimize the maximum error. And this is then the corresponding value that we choose as the minimum value for x. And then once we have that, we know what is the corresponding exponent using this formula here, and plugging in that minimum value that we have selected. So this is how it works out. And luckily, we don't have to do, I mean, we can do it also by hand or by Excel. That's possible. It's actually not that difficult. But of course, we don't have to do that. So in the last lecture, I will show you how to do that using real life data and the program using MATLAB. As I think you have MATLAB access here, you should have it. Otherwise, you need to contact someone from the software department. I think with your student credentials, you should have access to MATLAB. It's quite easy program actually, and there are pre-written codes. So the authors from here, Aaron Clauset, he has actually written a code for R, I think R, Python, and MATLAB. So you can choose what program you want to use. And so he has a program that gives you the corresponding minimum value and alpha for any data set. You just have to upload the data set, push the enter button, and what you get is the corresponding alpha and x minimum value using this methodology here. So you don't have to implement it by yourself. But it would be good, of course, if you understand the principle. Because you can do this actually the same principle for any kind of test. Okay? It's a general test procedure that you can implement for any distribution, basically. This is sort of the last resort. Okay? If you do not know what to do, you do that. Okay? So, using this methodology that I used, okay, and it's quite easy because you just have to push the enter button and you do it 5 times. Because I have 5 asset markets, so I push the enter button just 5 times. And then I get the corresponding estimates for the exponent alpha and the minimum value. Yeah? And what you see here is, okay, for the S&P 500, the alpha is 2.58. For gold, 2.66. For crude oil, 2.48. Dollar, for the British pound against the dollar, 2.6. And for Bitcoin, 3.02. We'll also here the corresponding minimum value for the realized variance. Okay, so that means so for instance here for the S&P 500, so values that exceed a variance estimate of 6.36 for those observations and larger, this power law rule applies. Okay, so in asset markets, and this is true for the return process and for the variance. Okay. We spoke about it last time already, and now we're operating with the variance. So all the observations are anyways just positive, right? So if the world would be normal, we would have this distribution. Okay, not allowing us for large standard deviations to occur. But in real life, this is not true. So we have in real life some part of the distribution is thin-tailed. Thin-tailed means, okay, like the normal, they are like the observations are close to the mean, but then there's a different rule that applies for certain observations that exceed this x minimum value. Okay, for these observations, a different rule applies. Yeah, and this is this power law, which means there's less probability here. But we have the tail. This is much longer. Remember, the standard normal or the normal distribution would tell us there are no six sigma events possible. Okay, but we have seen for the Dow Jones Index, 0.13% are larger than 6 sigma. And these are the impossible events. Okay, that have a very high impact that you will find here somewhere, that the normal distribution does not account for. So again, so all values that are above x minimum here, for these observations, there's a different rule. And that's this power law rule with an exponent of 2.58. That applies. So if you would, let's say, we can take it now already. So if you would simulate, if you would like to simulate that process, okay, what you would do is, okay, you would take the observations from the lowest, which is x1, until x minimum minus 1. Okay, that is your vector. Here are the thin-tailed observations. Here, okay, these are here. These are the thin-tailed observations that are in this area, and you have the observations that are here. They will be ruled by this law. So you can implement like a random number generator that is governed by that law. Okay? And you can store these in a different vector. And let's say, okay, 70% of the observations are here in the thin-tailed region, okay? 70%. And 30% of the observations are governed by this law. So what you could do is, you could have a random number generator that gives you a value of 1 when we are here in the thin-tailed region. So with a probability of 70%, it gives you a 1, and with probability of 30%, it gives you a 0. And what you do then is, okay, whenever but you have then sort of a binary vector, okay, 1, 0, 0, 0, 1, 1, and so on. So whenever you have a 1 in that vector, you grab randomly one observation from here, put it into a new vector, and whenever you have a 0 here, you grab an observation, you simulate an observation that follows this rule, and put it then in the second position of that new vector. Okay, so it's quite easy. It's quite easy to do this with a computer program. What you get then, you get a new data series that has the same properties, has very similar behavior like your variance series. So this is something what you could do basically with all of that stuff here. You can simulate how in real life the data would behave. And you see here also, so how many observations are governed by this power law rule. For the S&P 500, it's 5.96% of the variance process. For the gold, it's 6.72%. For crude oil, it's 12.22%. For the exchange rate here, 3.66%, and for Bitcoin, 4.78%. So it's a small fraction of the overall distribution, okay? But it's there, things are happening. So then, of course, you may ask, is the power law model a reliable representation of the data? Maybe it's a different distribution. Yeah? So you have your hypothesized model that you've estimated using this Kolmogorov-Smirnov test, right? And then you are wondering, okay, is this actually, it doesn't make sense given the data that I have. So to test your model, your selected model, this paper from Clauset proposes a goodness of fit test, which is based on D. So how does it work out? So we said earlier that given our single data series, yeah, we select the corresponding x minimum value and alpha that has the minimum distance of the maximum distances, right? So what we can do now, we can use our selected model estimates, our selected exponent alpha and x minimum, and we can simulate this series. We know that what are the corresponding values for alpha and x minimum because we have simulated it. But of course data is noisy, and you will get, and then for each of these data series that you have simulated, you can run this procedure. So you do this 1,000 times. You do this 1,000 times, and you get the distribution for this D, yeah, for the simulated data set. You get the whole distribution. You get 1,000 minimum distances of maximum distance for each of the simulated data sets. So they form a distribution, which we see here. So, and if your model, if your null model is true, yeah, because that's you simulate under the null hypothesis, yeah. If your null model is true, so here are now 2.5% of the data, and here are 2.5% of the data. So if if your original, from your original data set, if your D falls here within this interval here, from the simulated distribution of D, ds, okay, because it's simulated. If it falls herein, you would not reject your model. That's how it works out. So you would reject your null model when the D from your original data set is much larger than the simulated Ds. Yeah. So, and of course you operate with some significance level. Usually you have 5%. Yeah. So whenever your p-value from that procedure here exceeds 5%, you do not reject your model. Okay. You would argue that your estimated power law model sufficiently explains the data generating process. Yeah? But if the p-value is less than 5%, then obviously your model does not reflect reality. Okay? Your model is you would reject it. Then it's obviously a different distribution that generates the data. That's how you would argue. And you can use the same procedure here for any distribution. You can use the log normal or the exponential, whatever. So, and if you want to test, let's say you want to test the log normal distribution against your hypothesized power law model, you can estimate the p-value using this procedure for both models. And you would select the model that has the higher p-value. Yeah? This is what people are usually doing in practice when they operate with this kind of distributions. Because as I told you earlier, this kind of Kolmogorov-Smirnov test can be applied to any distribution. Yeah? It's sort of the last resort. And we see also here in table 3, yeah, let's take the other slide. Table 3, we see here the corresponding p-value of that implemented test. And again, luckily we don't have to do it by hands, okay? It would take eternity to do that. But so, and again, Klauset, he has provided this code on his web page. You know, we just have to push the enter button and then we get the corresponding p-value. But it's good if we have understood the principle. What is it all about? Okay. And here we see for none of the asset market variances, yeah, the power law model is rejected. So we accept the null hypothesis. So we accept our power law model as data generating process for all of these asset markets. And that's already an interesting insight. So what does it mean? It means markets are wild, wilder than people might have believed. And now we can use also hypothesis tests. Yeah? So Klaus et al., they derive, or they show, and that's actually quite the funny part here, that the alpha, of course, it has also a certain distribution, right? And the corresponding distribution, surprise, surprise, of the alpha is a normal distribution. So the exponent itself is normally distributed. Yeah? Something that you know already from OLS, okay? Because in OLS, everything is normally distributed, okay? If you run an OLS regression, everything is normal. But here, actually, if you use maximum likelihood estimation, the alpha is normally distributed. This is what the authors have been showing. But now it's important to remember, okay, it's derived under the assumption of independent drawings. Okay, in real life, things are not independent, but well. So, and using this assumption of independent drawings, alpha is normally distributed, and the standard deviation of that alpha is computed like we have it here. It's the exponent minus 1 over square root of observations that are governed by a power law, plus 1 over the observations that are governed by the power law. So it's a very simple formula. So for our example, for the S&P 500, what would it be? Well, the standard deviation is 2.58 minus 1. It's 1.58, right? Over square root of, and here we have, okay, we have 9,821 observations times 0.0596, right? So it's 1.58 over square root of what? We have 9,821 times 0.0596, because this is the number of observations that are governed by the power law. This is n, okay, plus 1 over 9,821. So, and that's then our the standard deviation of that exponent. Yeah. So that's how we can compute it for all the other guys as well, even for Bitcoin. So and now let's say, because Bitcoin had the only, so we know from the other guys they were in the middle, let's say, of between 2 and 3, right? So if we, once again here, for instance, S&P 500. So the standard deviation will be very low. I mean, I don't remember exactly what it was, but we can reject the null hypothesis that this guy would be 3. Yeah. So, and let's think about, okay, what does it mean? What does the value of 2.58 mean? So it means the theoretical mean of the variance process is defined, right? Because the theoretical mean implies, or it requires that alpha is at least 2. Okay, it is 2.5. But the variance of variance does not exist, because it requires that the exponent is larger than 3. And if we would take the distance, so if we would compute the standard deviation of the exponent here, and we would take the difference between 3, or the distance between 3 and 2.58, that's 0.42, right? And if we would divide that by the standard deviation of that guy, the t statistic would be much larger than 1.96. So we would reject that this guy here is 3. So it's really less than 3. Okay, it's really less than 3. Same is true for gold, crude oil, especially crude oil, and especially also here this US dollar. But Bitcoin, who knows? It's close to 3. Here it would make sense to make a test. Okay, is also for Bitcoin the variance of variance undefined, like for all the other asset markets? It would be surprising if it was, right? So this is what we are interested in here. So we test the null hypothesis. Under the null hypothesis, we argue no, Bitcoin's variance of variance is not defined, like for all the other asset markets. So the alpha of Bitcoin is under the null hypothesis less than 3. That's what we assume. And the alternative would be, okay, Bitcoin, the exponent is really larger than 3. So and for Bitcoin, okay, we know from the previous slide, the exponent was estimated at 3.02, and we have 114 observations that are governed by that rule. Okay? So we can then compute the corresponding value for the standard deviation, the sigma, and it's 0.198. So knowing that the exponent here is normally distributed, we can implement a one-sided t-test. Yeah? And one-sided t-test has a different critical value, yeah, than the two-sided test. And this is, of course, what you, of course, know from statistics classes. Okay, the corresponding value, if you test it, it's 1.65, because it's a one-sided test. Yeah? We are testing less than 3 against larger or equal than 3, so it's a one-sided test. And what is the t-test? How is it defined? Okay, we are interested in the estimated number, which is 3.02 minus 3, because that's our hypothesis. That's 0.02 over the standard deviation, and we know this. We have already calculated it. It's 0.198, and if you calculate it out, it's 101, and that's obviously much less than the corresponding critical value of 1.65. We do not reject the null hypothesis. What does it mean? Not rejecting our hypothesis means that Bitcoin variance behaves like the variance of the S&P 500 or gold or crude oil or British pound against the dollar. Yeah. Statistically, we cannot reject the hypothesis that the variance of variance is undefined. So statistically, this value here is less than 3. Yeah, and here once again I have written down what we had last lecture here. Okay, the theoretical second moment x squared. Okay, and x is now our realized variance process. Yeah. Provided that x is larger than the minimum value, yeah, this is how you would calculate it. Okay, and we know we need at least a value of 3. Yeah, because here, if that is 3, it's 0. Or if it's less than 3, it's undefined. Yeah? So it must be larger than 3 so that the variance of variance would be defined. So we see we can use these power laws for any kind of distribution. So we usually what people have done earlier, in earlier research, if you read research from the, let's say 15, 20 years ago, what people have been doing then, back in the days, the good old days, they used the absolute amount of an asset return. Or like Mandelbrot has done it in his 63 paper, he sorted the changes, the quantum price changes, into a vector of negative returns and a vector of positive returns. Okay, and then he was running some log regressions. And what people then have been doing afterwards, they have used the absolute amount of returns. Okay, so you just multiply the negative returns with -1. Okay, and then you get only positive returns, and then you can estimate the threshold, the cutoff, this x minimum value for your data vector. Because again, why are we doing that? Because power laws are only defined for positive values, right? So this is what people have been done earlier, yeah, and that's also what you can do, and you can make also inference based upon that. But what we will see, hopefully we can discuss this in the last lecture as well, because I have done that as well. And according to my experience, if you do that, you get somehow very large standard deviations, and it's difficult to make, let's say, give a precise or an accurate estimate of the corresponding exponent. Okay, if you use the daily data, so you have a lot of observations, and you use the intraday range-based variance estimator. Okay, you had very low standard deviation, and that's why you can make a very precise estimate of the exponent. Okay, so we can clearly say it's less than 3. And that's all we need to know. If you use these guys here, then because data is so noisy, it's tricky to make a precise estimate. So that's why I was using the range-based variance estimator. So what are the theoretical implications? Okay, again, that's how in finance people compute the t-test for some data, for some payoff, let's say. So according to theory, the second moment of the denominator should be close to 2k. If we standardize this, our payoff vector, that's sort of normal distributed, standard normal, and here what is here? We know it should be sort of a chi-square type distribution with 1 degree of freedom. So we know that if we take the square of what is here, it should be 2k. So that would be sort of the variance. We can think of it as the variance of variance. Yeah? This is sort of the variance of the payoff vector. If you take the variance of variance, this would be then something like 2k. So, and we do not even have to standardize the payoff, our payoff vector. This guy here, if the standardized version is finite, okay, this guy here will be finite as well. So, in finite samples, this guy here is informative. Yeah? So we can use it, and we can make inference based upon the t statistic. If the data is normally distributed. But our findings indicate, first of all, the data is not normally distributed, and it's not even chi-square distributed, so, because this guy here should be sort of a chi-square behaving, but we have seen the tails are much, much fatter than the chi-square distribution would suggest, okay? And we have estimated the power function, which obviously well describes our data. So our findings indicate, okay, the variance of that guy here, so the variance of variance is infinite or undefined because the exponent was less than 3 for the realized variance series. Which means in finite samples, the sample estimate is not informative. So in every sample, we get a different t statistic. This is what it actually means in practice. Every sample, we get a different t statistic. So only if the variance of variance would exist, then this guy here would be informative. And we could use the t statistic for making inference. So what are the theoretical implications? So we spoke already about it earlier. So he argued, the Taleb argued in his book on statistical consequences of fat tails. He noted that for exponent of alpha is equal to 3, even then the central limit theorem operates very slowly, and we would need the observations to be of order 10 to the power of 6. So 1 million observations are required so that inference derived from the central limit theorem becomes acceptable. And as the economic magnitude of the power law exponent decreases, so the more we move to 2, to a value of 2, the more observations we need. And this is non-linearly increasing. But in real life, we don't have so much data. So we spoke last time about the Pareto distribution, the classical Pareto distribution, that has an exponent of about 2.1 or 2.14, to be more precise. So for that kind of distribution, okay, we know the theoretical mean exists. It exists. We know that because alpha is larger than 2. Only slightly larger, but it's larger than 2, so the first moment is defined. But the variance is not defined. Okay? So how many observations do we need so that our sample would give us an informative estimate of the mean? So we would need 10 to the power of 11 observations. I don't know that number. It's, I don't know, trillions, maybe billions. So we don't have so much observations, okay? So in finite samples, we do not observe the mean of this kind of distribution. So what about correlation or correlation-based metrics or estimates? Well, we have seen in the first lecture, okay, that we can rewrite that covariance, correlation, and variances, they are related to each other, okay? So point estimates. So what is in the numerator and in the denominator? Yeah? We can rewrite this guy here, the beta estimate from your regression model, so that we have in both a denominator and denominator functions of the variance, market variance or the asset variance. So point estimates derived from OLS are functions of asset variances, and therefore they are uninformative. Because in every sample, we have a different value. Okay? And then you will probably you might have encountered something like dynamic correlation models. Okay, it actually tells you that people do not know much about correlation. Because they get for every sample a different correlation. So what does it mean? Not much. You cannot use it in real life. And there's a paper, recent paper from Descent. It's published in the JFE, Journal of Financial Economics. Okay, and they conclude that when we now consider the corporate finance side of finance, which is actually not my expertise, but this paper is about per capita budgeting, and in capita budgeting, what model do you use? You still use the CAPM, right? And some people use also Farmer and French factor models nowadays. So, but still, these in capital budgeting, people rely on these standard methods, okay, derived from OLS also. So they conclude that acquirers experience significantly lower cumulative abnormal returns when announcing bids for low rather than high bidder targets. And the authors estimate that using the capital as a pricing model in this context leads to valuation errors between 12% and 33% of the deal values. But that's a lot of money, right? That's a lot of money. And also here, we can also consider that the replication failures that are documented in the study from Hu et al., that the reason for that is that the variance is sample specific. So t-statistics, even a t-statistic of 2.78, has no meaning. So obviously, because correlation as a metric is uninformative, because we have seen in every sample you got a different estimate, so you cannot use it. Okay, you want something that you can actually that also holds in next sample, right? Otherwise, what would you do with that? So because correlation is uninformative, we need obviously a new metric that measures the codependency of two random processes, let's say stocks, or risk in terms of variances, okay? So the concept of correlation appears to be the cornerstone of modern finance and it is applied in almost all finance-related research studies. But we have already talked about it, that Farmer himself argued in the 63 papers that if the population variance is infinite, other statistical tools like OLS, which are based on the assumption of finite variance, will be either considerably weakened but rather give very misleading answers. So this study, this is my own study, published this year. I showed in the study that the foreign exchange rates, that foreign exchange rate variances, again I use this intraday range-based estimator, are governed by power laws with exponent less than 3, like I reported in the other study, okay? But now for the G10 currencies. And it suggests that the second moment, so the variance of variance is infinite for all of these G10 currency variances. And I derived a new concept to measure codependencies of power law processes, which have this kind of tail exponent. Yeah? And this measure of codependency, I termed it cofractality. And I show that risk diversification based on the concept of correlation will indeed give misleading answers. And I showed that actually in a table, okay? I provided two subsamples, and I showed that the results are completely different if you use correlation. So what's going on here in this study? So I come up with two definitions of fractality or cofractality, and yeah, it may be a little bit difficult to grasp the concept. Okay, so we have cofractality in its strong form and in the weak form. So what I basically write down here is, okay, it actually means nothing else than, okay, we have two distributions. Okay, one part of the distribution with probability, let's say p, is thin-tailed, and with probability 1 minus p, it's fat-tailed. Okay, and we have two random processes here that follow this rule. This is what it says, nothing more than that. But you know, in these journals and so, they like to have it a little bit more fancy, so that's why I came up with this definition. So, and similar, we have two definitions of weak and strong form. So, and these images actually tell you the whole story already. So let's say we have two distributions here, yeah, and whenever the distribution is here white, then it's obviously in a thin-tailed regime. Yeah? When it's gray, dark gray or light gray, then these observations are governed by a power law. Here on the left-hand side, we have strong cofractality. What does it mean? So all this you find in the study. Okay, all this you find in this study. I just copied it here to my slides. So what we see here is, first of all, both distributions here have the same amount of observations that are governed by a power law. Okay, and it doesn't need to be exactly the same amount of observations, but roughly the same. Because how is cofractality defined? It is that more than 50% of observations from the distribution that has the larger number of observations in the power law regime should coincide with observations in the power law regime from the other distribution. And this is what you see here. Okay, so we have here two processes. Okay. Process 1, here we are in a thin-tailed regime, and all of a sudden we are in this extreme regime where we have this extreme movements, then again we are in a thin-tailed regime. Okay, and then we have another distribution. This is here the timeline, okay, and this behaves similar. Okay, here we are all of a sudden in the extreme regime, and here we are again in the thin-tailed regime, and maybe here we are again, maybe a very short time in the fat-tailed regime, in the power law regime. And here we see, okay, these observations here coincide. Here we have in both distributions observations that are governed by a power law process. And if we have more, let's say, we have in total, the first distribution has in total, let's say, 80 observations in the power law regime. And the second distribution has maybe, let's say these are 60, and here we have 10, let's say 70. Okay? But 60 coincide. Yeah? So this means, according to my definition here, that here we have the presence of strong cofractality. Yeah? Because it's more than 50% of the observations of the process, and 50% would be here 40, okay? Because of the process that has more observations in the power law regime, which is the first one, which has 80. 50% of 80 is 40, but we see that 60 of the observations coincide. And 60 is more than 40, So here we have the presence of strong co-fractality. So they at the same time, or roughly at the same time, they generate these extreme moves, these two processes here. But not always we have processes that have roughly the same number of observations that are governed by this power law regime. It can also be that we have one process that has much lower number of observations that are governed by a power law regime, right? And the other one has a lot of observations. So we need also a definition for this kind of situation. And this is what I term weak cofractality. So now, you see here, more than 50% of the observations from the process that has less observations in the power law regime should coincide. This is exactly what happens here, okay? The first distribution here on the left-hand side has so many observations in the power law regime, and the second one, so many. But here they coincide. They're at the same time in the power law regime, and this is more than 50% of the total observations from distribution 2 in the power law regime. And it's a very simple concept, very simple, because we are not, that has nothing to do with correlation. Okay, we have a binary vector. Okay, we can transform this distribution here into a binary vector that has zeros whenever we are in a thin-tailed regime, and when we have when x is larger than x minimum, okay, then we know we are in the fat-tailed regime. Then it gets a value of 1, and here gets a value of 1, and here again we have values of zeros because we know we are in a thin-tailed regime. The same we do for the other guy. Binary vectors consisting of zeros and ones. And then you count the number, you multiply these vectors, and this gives you then sort of the number of observations where they coincide in the power law regime, okay? Very simple, very simple. But powerful. It's a powerful measure for codependence. Without using correlation, that doesn't work. And also, if you want to make hypothesis tests, because this is a binary measure, you need to. I derived it in my paper how you would implement hypothesis tests. Okay, so you can just go through it. Yeah, so it's not that difficult. And here I give you two examples of the absence of cofractality. So it's a similar distributions like in the previous example. Okay. We have the same number. We have here two distributions that have a very similar number of observations in the power law regime. Yeah, but here we see that less than 50% coincide in the power law regime. So here we would say this co-movement here, or this co-dependency can be just purely by chance. Okay, it's just 10% or so, or even less. It's less than 50%, so this can be throwing a coin. Okay, if you have to throw a coin, it's in my definition it's just a matter of chance. So cofractality requires you want to have the likelihood larger than purely by chance. So that's why I have defined it, because one of the reviewers he was wondering why 0.5 as the critical value. Okay, because if it's less than throwing a coin, if less than throwing a coin of the observations coincide in the power law regime, this can be just a matter of chance. There's in my opinion no systematic behavior. But if it's more than 50%, it's not a matter of chance. But then of course we have to see, okay, is it significantly? Is our cofractality measure, is it significant? And then we have to implement the test statistic, which is derived from a t-test, but we have to take the distribution of these binary vectors into account. This is what I also defined in the paper, and that's actually quite simple. Here, right-hand side, we have the absence of weak cofractality. Yeah, so we see we have distribution 1 has many observations in the power law regime, yeah, and distribution 2 has fewer. But less than 50% of the distribution that has fewer observations in the power law regime coincide here. So here we have the absence of weak cofractality.
So sample size on this somehow, like minimum sample size might make a false negative over the sample size. You start having if you have a larger sample, it seems like it'll be more relevant, and then if you have a smaller sample, then it might be not so definitive.
So in order to here it's quite obvious, because here we have the second distribution has less observations.
Because I'm just thinking naturally that there may be more correlating with certain events, and if you take a longer timeline, then you may have the correlating events and the non-correlating events kind of getting washed out. Makes sense?
I'm not sure about that. I mean, first of all, we have here a lot of observations, and of course, all of these measurements. The uncertainty we account for in when we run the hypothesis test, right? So here we wouldn't even run the hypothesis test, because the coefficient would be less than 0.5. So here we wouldn't even run the test. But here in the other example, here we would run the test, and we would take into account the uncertainty in the test statistic, because obviously it's a binary variable, right? So this takes into account the uncertainty that we have if we have fewer observations here that are governed actually by the power law. So the statistic becomes, of course, less significant if the sample size decreases. So it's always better. If you have the more observations you have, the better. And here we have then this. You can hardly see it probably, but well, we have here then this matrix where I calculated the coinciding observations here in the power law regime and the total number of observations in the power law regime here. And then we can, based upon these numbers, I could compute the strong cofractality matrix and the weak cofractality matrix. So, and we see here that there's a high level, if we just consider cofractality in its weak form, which is perhaps more relevant for practice, because it's unlikely that two assets have a very similar number of observations that are governed by some power law process. So it's more likely this weak form of cofractality is most likely more interesting for practitioners, right? So and here we see we have a high level of codependence using the cofractality measure in its weak form. Yeah, we have the highest value is here. I think it's 0.94. So and you see a lot of 3 stars, which means they are significant on the 1% level. Yeah. So the codependency is significant on a 1% level. And here your question concerning the sample size. Here you see we have here a value of 0.53. Yeah, which over here 0.55, 0.54, and obviously we have the sample size is too little. That's why here they are not significant. They are not significant. So values must be, they must exceed, was it 0.6 or so that we can talk about significance here. So that's here we can say it's just noise. The codependency is just noise. We would, even though it exceeds 0.5, but because there's uncertainty because of lacking observations, here we would not. Here we would say it's insignificant. The cofractality is insignificant. But this is something that I came up with. It's published also in a good journal, High Impact Factor. The impact factor is also interesting. The impact factor of that journal here, the International Review of Financial Analysis, is as high as the impact factor of the Journal of Financial Economics, which people regard as the top journal, right? But you see also some, in academia, okay, people are a little bit, let's say, not so flexible. let's say, not so flexible. In the industry, I worked at Klarna. It's a big company in Stockholm before I came to academia, and people I mean, it was back in the days, okay, but anyways, it was a fast-growing, it was back then the fastest-growing fintech company in Europe, and people were very flexible, okay. Every week, you got new work tasks, and the working environment has changed. You know, every week, there were all the day, there were always something new going on. And you have to be very flexible in your mindset in order to, you know, keep in touch with in that working environment. Okay, so it was really tough, but interesting, of course. And I mean, if you're open-minded and so on, and then it's fine. And some people really enjoy that. But in academia, it's a little bit different. Okay, first of all, we might have already recognized that people they cannot think about outside the box of variance and mean. They need the mean variance space so that they can think and do their work. Whenever they get out of the comfort zone, so whenever they get out of the variance zone, okay, they get, let's say, they become defensive. Because what does it mean? It means that what they have been doing makes no sense, all right? So in a way, you can understand it, the behavior. But on the other hand, okay, if you're interested in the truth or are you interested in storytelling? I mean, you can decide, okay? I'm rather interested in the truth, and if I make a mistake, then I have to stand for it, all right? So that's and also it's this kind of journals, okay? People consider these three journals as the top-notch journals, okay? Even though they publish nonsense, it doesn't matter. Anyways, they regard it as the top-notch journal. And disregard that other journals are on the rising edge, okay? This journal has a higher impact factor than the Journal of Finance nowadays. So this environment is also dynamic. Okay, it's not written in stone that the Journal of Finance is the most important journal in terms of citations or scientific impact. No, it's not. Other journals are on the rising edge, but there are many people in academia they just don't get it. They don't get it. They don't understand that also journals are the impact of journals is dynamic. It's not written in stone. Like the concept of correlation. Okay, there are other things, okay, that are on the rising edge. That's also why I put this subheading here, okay? Truth, or more precisely, an accurate understanding of reality is the essential foundation of any good outcome. Most people fight seeing what's true when it's not what they wanted to, when it's not what they wanted to be. And it's actually Ray Dalio. I don't know if you know Ray Dalio. It's you can Google him. He's the founder of Bridgewater Associates and author of the book Principles. He has written many books nowadays. So he is he's the most successful hedge fund manager, running the largest hedge fund in the world that is successful over, I think, already 25 years, which is very, very unlikely to be a coincidence. Okay, so he knows what he's doing, obviously. He was also helping the EU for when they had in 2009 the problems with Greece, okay, the European debt crisis. Okay, he was consulted back then. He is one of the richest men on Earth, I think, in the top 100 richest men. But it's maybe not surprising if he is running this hedge fund for many years. And so he's a practitioner who knows what he's doing. Obviously, knows what he's doing. And so that's a quote from his book, and I think that is true. So you need, if you want to have a good outcome, you need to get an accurate understanding of the truth, of what is real, of the reality. But many people they refuse. They refuse. They do not want to know the truth if it's not what they want it to be. Okay. If people want to have correlation and if they want to have the variance, then they will refuse the scientific fact that the variance is maybe not there or uninformative. So yeah, that this is the lecture for today, and I also want to say that in the last lecture I will So most important thing is that I will give you some hints for the assignment. So we will hopefully I will until then have some examples that we then discuss, that you know what you can expect and how to answer this answer these questions. Okay. You can also use this what was it called, GPT or yeah, you can use that as well. That's no problem, because he cannot solve that question anyways. But
The variance there is too high.
yeah, exactly. So yeah, we will come up with, we will discuss some examples that are related to all what we discussed, and then next lecture I think we will deal with dependencies, because obviously we need a new measure for dependency. If the correlation doesn't exist, right, then we will consider a new measure for dependency. Now we have discussed codependency, okay, codependency in terms of this power law behavior, but dependency is something different, and this has it is also related to the exponent, but this is something that we will hopefully discuss then in the next lecture. Otherwise, have a good weekend.
Thank you.